So today we are going to begin the numerical parts, which is based on instruction level pipelining, in which we will learn how to calculate the pipeline cycle time, non-pipeline execution time, speed up ratios, pipeline times, sequential times, and throughput. We have already discussed the formulas for these terms and parameters. So let's begin with the problem 1. I am reading out the problem 1, which defines that if we consider a pipeline which is having the 4 phases with duration 60, 50, 90 and 80 nanoseconds, and given that the latch delay is 10 nanoseconds, we have to calculate at first the pipeline cycling time, non-pipeline execution time, speed up ratio, pipeline time for 1000 tasks, sequential time for 1000 tasks, and throughput. If we move towards the first, that we have to calculate the pipeline cycle time, it is given that the 4-stage pipeline is used and the delay of stages is also given. The values are 60, 50, 90 and 80 nanoseconds, and the latch delay or the delay due to each register is 10 nanoseconds. So for the first part, we can calculate the pipeline cycle time, that is equals to maximum delay due to any stage plus delay due to its register. So the maximum of 60, 50, 90 and 80 is 90 plus delay due to its register is given 10 ns. So 90 ns plus 10 ns equals to 100 ns. We move to the part second. We see that non-pipeline execution time for one instruction is 60 ns plus 50 ns plus 90 ns plus 80 ns, which results into 280 ns. Moving to the third part, calculating the speed up ratio. Speed up is equals to non-pipeline execution time divided by pipeline execution time. We have calculated the value of non-pipeline execution time in the part 2, which is equals to 280 ns, and divide by cycle time. The cycle time's value is 100 ns, so we divide 280 ns divided by 100 ns is equals to 2.8. Moving to the next part, calculating the pipeline time for 1000 tasks. So it is equals to time taken for first task plus time taken for remaining 999 tasks. So the value is 1 into 4 clock cycles plus 999 into 1 clock cycle. So 4 into cycle time plus 999 into cycle time equals to, we know the cycle time is equals to 100 ns, so putting the values we get 4 into 100 ns plus 999 into 100 ns, which is equals to 400 ns plus 999 ns, which is equals to 1,003,000 ns. Moving to the next part, while we calculate the sequential time for 1000 tasks. Non-pipeline time for 1000 tasks is equals to 1000 into time taken for one task is equals to 1000 into 280 ns. We are simply putting the values now. It is equals to 28,000 ns. Moving to the last part of first problem, to calculate the throughput. The throughput for pipeline execution is equals to number of instructions executed per unit time, which is equals to 1000 tasks divided by 1,003,000 ns. In the problem 2, we can see a 4-stage pipeline that has the stage delays as 150, 120, 160 and 140 ns respectively. Registers are used between the stages and have a delay of 5 ns each. Assuming the constant clocking rate, the total time taken to process 1000 data items on the pipeline will be, we have the 4 options: 120.4 microseconds, 160.5, 165.5 and 590 microseconds. The solution we move, it is given that the values are these. So while we calculate the cycle time, it is equals to maximum delay due to any stage plus delay due to its register. So the maximum out of 150, 120, 160 and 140 is 160 ns. plus 5 ns is equals to 165 ns. So the value of cycle time is 165 ns. While we move to the pipeline time to process the 1000 data items, it is simply time taken for the first data item plus time taken for remaining 999 data items. It is equals to 1 into 4 clock cycles plus 999 into 1 clock cycle. It is further 4 into cycle time plus 999 into cycle time. Putting the values of cycle time that we have calculated, it is 660 ns plus 164835 ns, and the total comes as 165495 nanoseconds. Converting that to the microseconds, the value is 165.5, so the option C is correct. Moving to the problem 3, consider a non-pipeline processor with a clock rate of 2.5 GHz and average cycles per instructions of 4. The same processor is upgraded to a pipeline processor with the 5 stages, but due to the internal pipeline delay, the clock speed is reduced to 2 GHz. Assume there are no stalls in the pipeline, the speed up achieved in this pipeline processor is. We are again having 4 options: 3.2, 3.0, 2.2 and 2.0. So while we have to calculate the cycle time in the non-pipeline processor, we have given frequency of the clock is 2.5 GHz and the cycle time is 1 divided by frequency, and the value of frequency is 2.5 GHz, so it is 1 upon 2.5. Putting the value of giga equals to 10 raised to power 9, we get the result as 0.4 nanoseconds. Calculating to the non-pipeline execution time, the formula is number of clock cycles taken to execute one instruction, which is equals to 4 clock cycles. Putting the values, we get 4 into 0.4 ns, which is equals to 1.6 nanoseconds. Moving to the next part, cycle time in pipeline processor, the frequency of the clock is 2 GHz. Again we know the cycle time is 1 divided by frequency. Putting the values of frequency is 2 GHz. Converting the value of giga is equals to 10 raised to power 9. So putting the values, we get the cycle time in pipeline processor equals to 0.5 ns. Again, calculating the pipeline execution time, since there are no stalls in the pipeline, so ideally one instruction is executed per cycle, so the pipeline execution time is 1 clock cycle, which is equals to 0.5 ns. Calculating the last part, speed up is equals to non-pipeline execution time divided by pipeline execution time, which is equals to 1.6 ns divided by 0.5 ns, which is equals to 3.2. So we can see that the value is equals to 3.2, so the option A is correct. Moving to the last problem, problem 4, we are reading out that the stage delays in a 4-stage pipeline are 800, 500, 400 and 300 picoseconds. The first stage is replaced with a functionally equivalent design involving 2 stages with respective delays 600 and 350 picoseconds. Now we have to calculate the throughput increase of the pipeline is percentage. So you have to calculate the percentage for the throughput increase of pipeline. The solution is the execution time in 4-stage pipeline. The cycle time is equals to maximum delay due to any stage plus delay due to its register. So the maximum value out of 800, 500, 400 and 300 is 800 picoseconds, and the delay is given as 0. So the value is equals to 800 picoseconds. Now we are moving to the throughput in the 4-stage pipeline. The throughput is equals to 1 number of instructions executed per unit time equals to 1 instruction divided by 800 picoseconds, and the execution time in 2-stage pipeline. Cycle time is equals to maximum delay due to any stage plus delay due to its register, and the maximum out of 600 and 350 plus delay is 0. So out of 350 and 600, the maximum value is 600. So the result is equals to 600 picoseconds. The throughput in second stage pipeline, the throughput is equals to number of instructions executed per unit time is equals to 1 instruction divided by 600 picoseconds. the final part has to be calculated, that is throughput increase, which is equals to final throughput minus initial throughput divided by initial throughput into 100. We have all gathered all the values. Just putting the values, we can calculate the final value of throughput increase. Putting the values and making it simplify, we get the result as 33.33%. So this was all about today's lecture, in which we have learned that how to calculate the various parameters of pipeline and non-pipeline execution, like speed up, throughputs, efficiency, etc. Thank you.